All right, so I'd like to introduce Andrew Younge, who is a PhD student at Indiana University, who's working this summer at ISI, which is part of USC, which is in Southern California, but he's working in Washington, their Washington office, and he will talk about some aspects of GPUs on clouds. If you're interested in GPUs on clouds, I would note that Futuregrid does have a small cluster with GPUs, which is designed precisely to address this issue. So it's available for experimentation. You need to write a project, of course.
So thank you, Jeffrey. As he said, my name is Andrew Younge. I'm a PhD student at IU, but currently this summer as a visiting researcher at ISI East. So I'm going to talk a little bit about GPUs on clouds. Hopefully I won't keep you guys too long. I know it's Friday afternoon and everybody's probably excited to go enjoy the nice weather. So, well, depending on where you are in the US, I guess. So I'll do a quick introduction to infrastructure as a service and how it pertains to GPUs. Talk a little bit about how to program GPUs only from a very, very high level, and then dive into actually providing GPUs or graphics processing units, for those who aren't familiar with them, within a cloud infrastructure. We'll talk about various options that we have, the design that we choose, as well as the current work in progress in terms of implementation. Look briefly at performance that we've seen thus far, and then we can talk a little bit about what this means for scientific cloud computing. So and feel free to stop me at any point in time if you guys have any questions. I'd be happy to answer. So first and foremost, I'm just going to try and frame where we're talking about in the whole cloud perspective. This talk is going to focus mostly on infrastructure as a service and the underlying hardware, thereby providing that hardware to infrastructure as a service that can then be leveraged by platforms and software as a service. So this gives you a broad view of where we're interacting, and the idea is that if we change fundamentals at a base level, they can percolate upwards and actually have a notable impact on various new and upcoming software tools. So just briefly, we can talk about conventional CPU architectures. Most of you guys who have ever taken a computer architectures class should be very familiar with that. You have within a normal CPU various control logic structures and an ALU, along with various level 2, level 3 caches that try to mask the latency between CPUs and your main memory. The idea is the ALU is not that large, and that it's mostly concentrating on a single thread or a small amount of threads executing rather quickly. Now obviously it's much more complicated than that with out-of-order execution, branch prediction, all that stuff. So this is a very, very high level. But even at this level we can see a notable contrast between CPUs and GPUs, where you can think of many small threads as small ALUs with local caches, which are then tied together through a larger bus that actually connects to the CPU. This is actually, excuse me, the idea is that you want to be able to put bandwidth and do put a lot of your data quickly through utilizing maximum amount of bandwidth, and do things in parallel as quickly as possible, which is a little bit of a reverse perspective than a normal CPU architecture. So in terms of writing your code, it's a different story entirely. Normally you just have host code which runs on your CPU, and you do your computation. Within this model you actually have host and device codes, where each device has a set of blocks where you actually execute, at least in terms of CUDA, these kernels. And the idea is you pass your data from the host to the device. So it's important to draw that distinction for a couple of reasons, which we'll see a bit later. But it should be noted that you are moving your data to a specific place. Again, just to briefly go over the structure of GPUs, you have multiple blocks within a grid, and your kernel maps to a grid. Within a given block, you have multiple threads, and you identify each one of these based on your kernel or your block ID and your thread ID. And again, this is very simple. I recommend everybody, if you're interested if you haven't already, look at the CUDA programming manual. It's excellent and goes much more into detail on how to actually program, which, again, I'll talk really briefly about from a very high level. But the interesting thing here is that you actually, to do your computation on the GPU, you have to move your data from CPU's main memory to GPU memory, and vice versa to return your results. This is a little bit different than any given multi-threading scenario, so which a lot of times will use cache mechanisms to miss CPU main memory entirely. But here we actually have to explicitly move data to and from the GPU. Again, I'm trying to go quickly through here. Programming model. Well, first, it's interesting to note that GPUs were originally designed for dealing with image data on displays, running your latest game on your workstation, for instance. There's also workstation and AutoCAD tools that take advantage of this. But it turns out the way in which you do that computation works well and maps well into many scientific computing problems. The idea here is that we're leveraging the idea of SIMD or SPMD, where you write a single instruction or program and it actually executes multiple times. As you can see here, if we have a vector and we want to add some constant k to it, you have multiple ALUs which your single instruction, take a vector and add k to it, gets broken into pieces and executed in parallel, if you will. Again, this also shows it in a more specific CUDA sense, where you actually use your block ID and thread IDs specifically to figure out which piece on the vector you're actually doing your computation on. This is very broad. Definitely look at the CUDA programming manual for more details. But today there's a number of, at least a couple of different possibilities in terms of GPUs and GPGPUs, general programming GPUs. NVIDIA Teslas, or NVIDIAs in general, are the most common. There's also the AMD, what used to be ATI Radeon cards. And it originally started with CUDA, where NVIDIA allowed users to write a modified C language, if you will, with special CUDA instructions, and it would execute on the GPU. There's now the OpenCL, which is an open platform to support this same model of computation, and maps both to AMD graphics cards as well as NVIDIA Teslas.